Welcome back to geometry. We want to continue taking a look at section 19 on similarity. In the previous video, we introduced similarity and took a look at one of the theorems, which we did not prove. And I'd like to make a couple of comments about that theorem again before we move on, and then look at the theorems for similarity conditions for triangles. So this theorem, the basic proportionality theorem, if we have a triangle, then we have, for some triangle ABC, we have that the line passing through DE is parallel to AC if and only if we have these collection of equalities. Now, it's going to be the case sometimes that we use the fact that DE is parallel to AC to get merely one of these equalities, and that's all that we need. And that's fine. We'll do that in the following theorem. We won't use all of them, we'll just use one of them, and that's okay. And then working the other direction, so that was the forward direction, assume this and we use whichever of these we desire to use. Going the backwards direction, it only takes one of these equalities, right? It's this one, or that one, or that one, and we can immediately move over to here and say that the two lines are parallel. So it's not often that, well, I mean, I guess I don't really know for sure, but I think that what we'll end up doing is we'll end up using let's see here. Well, let me take a look. I know that we want parallels, yes. So we'll use the parallels to get the equality of these, at least in this theorem here, in the proof of it. So just keep that in mind. Once you have parallel, you can use any one of these that you like, and as soon as you have any one of these, you may conclude a parallel. So we'll go ahead and take a look at our first similarity condition. Now we looked at congruence conditions in the past for triangles. What conditions would be sufficient for us to conclude the congruence of two triangles. Side angle side was one of them, side 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 was another, and angle angle side was another one. So in this section, right, we're just looking for similarity. So we don't actually, right, we don't need the congruence of sides. We only need the congruence of angles, and then the appropriate ratio for the side lengths. And what it works out to be is that as long as we have the three angles matching, then we would have similarity of the triangles. And that's what we want to show here. So given two triangles, if each of the angles are congruent, right? A is congruent to D, B congruent to E, C congruent to F, then the two triangles are similar to one another. All right. So let's consider this figure for our proof. And what we're going to want to do is we're going to want to, of course, assume that the angles match appropriately, that they are congruent. And then there's one additional thing that we'll want to utilize. We're going to assume that it's triangle ABC that's larger than triangle DEF. And when I say larger, I mean that the corresponding sides, AB, is longer than DE. When we do that, we can go ahead and find a particular parallel line. Find a line parallel to AC, but we're going to choose it so that way the value, sorry, I don't want D there. I want it to correspond to D, but let's use G. If I choose this point G carefully, such that the distance from B to G is the same as the distance from D to E, then I get that this triangle and that triangle are congruent. So I get the equality of side lengths, which I would like to have. And since this guy, we chose that to be parallel, we have several equivalencies we can choose from for ratios. So we'll be able to utilize this theorem in our proof. So find a parallel show congruence. And then once we show congruence, we can use the basic proportionality theorem to get us our first equality of ratios. And then we will show, or we'll then be able to conclude that the two triangles are in fact similar. So first, of course, the givens. Angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. So those are the assumptions that we're making for the angles. The other thing that we wanted to do is we wanted to assume that AB is larger than DE. AB is larger than DE. Now we can assume that without loss of generality because one triangle is going to be bigger than the other. If that's not the case, then they're simply congruent, which is a stronger condition than similarity anyway. So, so we don't need to worry about equality of side lengths. We need inequality of side lengths, so assume that this one is bigger. So these are the givens. All right. The next thing we can do is we can find the point G. There exists a unique point G on the line segment, in particular the ray from B to A. So I'm coming out from B, it's somewhere along here, such that we get the distance that we want. The distance from G to B is the same as the distance from E to D. All right, and we know we have that because of the ruler postulate. All right, so we then have that AB is larger than GB. AB is larger than GB, and that's because we're making the simple substitution of line 2 into line 1D. Excellent. Once we have that, of course, we can conclude that G is between A and B. Right, we drew it that way here because we know it's going to be true since BA is larger than ED. So awesome. And between this inequality. Excellent. All right, so now that we have this point, we can claim that the parallel line exists. So there exists line L, which is parallel to AC and through the point G. So this is the line L. And that's by the parallel existence theorem. All right, once we have that, we can take a look at where L intersects BC, but we want to be very clear as to why this line intersects BC, and it's because it does not intersect AC and Pasch's axiom, which I believe is actually a theorem. So L does not intersect AC. Excellent. So since we have a line that comes in through side AB, it must pass through one of the other two sides. And because it is not AC, it must be BC. So it does not intersect AC by the definition of parallel. So then we have that L intersects BC, we'll call it at point H, and that's by Pasch's theorem, or Pasch's axiom. So we'll call that point H. All right. Once we're there, we actually have enough to be able to talk about the previous theorem, right? We have the conditions necessary. We have a triangle and parallel lines and labels for G and H. So we could talk about these proportions or these ratios, but we don't want to do that yet because we also want to be able to take those ratios and connect them back to the side lengths for our second triangle. So we want to show congruence of this upper triangle with this triangle first. So to do that, let's recognize that this angle and this angle are the same. So a couple of angle congruences here. So angle 1 is congruent to angle BAC. And that's by the converse of the corresponding angles corollary. Excellent. Then we've got, all right, we want to connect that back over to here. So angle 1 is congruent to angle D. I suppose I didn't need to use BAC there. I could have just used A. That's quite all right. Anyway, angle 1 is congruent to angle D, and that's by the transitive property of congruence. So angle BAC there, I didn't need BAC, I just could have called it angle A. That's not ambiguous. All right, so that gives us angle, side, angle. So we have that triangle. Let's see, let's call it GBH is congruent to triangle DEF by angle, side, angle. Where the first angle is, we can call it B is congruent to E, so that's 1B. And then the side we found, so that's by number 2. And then we have, let's see here, we have this angle, so that would be number 9, line 9 there. Excellent. So angle, side, angle gives us congruence. All right, so now that we have the congruence of those two things, the key thing that we want to take away at this point is that BH is equal to EF, or that HB, right? Order doesn't matter. HB is equal to FE. There we go. That's by the definition of congruence. Of triangles. Okay, so now let's go ahead and connect it back to the previous theorem, the basic proportionality theorem. Since I have parallel lines AC and GH, I can conclude, all right, the desired ratio here is side length to side length. So I can say that BG over BA or GB over AB is equal to HB over BC, let's call it. I mean, it doesn't matter anyway. So 12. We've got let's call it GB over AB is equal to HB over CB. And that's by the previous theorem, basic proportionality theorem. Basic proportionality theorem. But we have several equivalencies, right? GB is equal to ED. So this is ED over AB is equal to, and we have that HB is FE. So this is FE over CB. And that's by a substitution of both lines 11 and 2 into line 12. Okay, so we have this equality here. Now, if I wanted to, which wouldn't be a bad idea, I could repeat this entire process. And I could repeat the process instead of using this guy, right? I could consider some point over here and a parallel line to BC. And that would give me this triangle is congruent to this one. Okay, that's what I'm looking for. A to here is equal to D to E. If I were to do that, then I would get that A to G, call it. A G to a B is congruent to, or sorry, let's call it DE over AB is equal to DF over AC. Excellent, there we go. So I got two pairs of sides. Right, I got this side and this side with this side and this side. I'd have to repeat this process one more time to get one of these two sides along with the bottom here. Okay, so I've got to pull in that side as well. So I'd have to repeat this entire thing. So rather than repeating the entire thing, I'm just going to say that in a likewise fashion, we have that DF over AC is equal to ED over AB. And that would be using the red line here. We already showed that ED over AB is equal to FE over CB. So we have the required conditions for similarity. Equal angles, right, congruent angles, and the proportional side lengths. So triangle ABC is similar to triangle DEF. All right, excellent. So we have our first similarity condition for triangles. There are others. Let's take a really brief look at a couple others. First of all, remember that a couple of sections ago, we talked about that the sum of the interior angles of a triangle add up to 180 degrees. So if I have measure of angle A plus measure of angle B plus measure of angle C is equal to 180 degrees, then as soon as I have two of these angle measures, then the third one is fixed. I don't have any options for C, right? If A and B are given, then I know what C is too. And because of that, all I need for similarity is two angles next to each other that are congruent. So for triangles ABC and DEF, if we have two angles are congruent, we immediately get that the triangles are similar. We don't need that the third is. If we wanted that the third is, we would just say, hey, look, here they are, they're equal to each other. All right. Another option for us, a couple other options, if we wanted to put in what would probably be a little bit more work in many cases, but a couple other conditions that we could use. If we have two triangles, ABC and DEF, if we have that angle B is congruent to angle E, and, right, so if we're looking at two sides here, so we have side angle side and side angle side, right? Complete our triangle, right, the angles we need to be congruent, but then we want to have the appropriate ratio for the sides. So we would say AB over DE is equal to BC over EF, having the appropriate, right, the sides have the appropriate relationship, right? They're proportional. If we have congruent angles and the adjacent sides are proportional, then the triangles are similar. A notational concern here, we have side angle side congruence condition for triangles, and we want to make sure that we are referencing them differently. So side angle side congruence is going to be referred to the same way that we have been, and side angle side similarity will be referred to as side angle side similarity. So SAS sim for short. And then what we would be looking for is right, a congruent angles. That would be one of the things we have to show, and the other thing we have to show is the satisfaction of proportionality. So when we talk about side angle side congruence, we have three things to fill in: side, angle, side. When we talk about side angle side similarity, we have two conditions to satisfy: congruent angles and the proportionality. All right. So side, side, side similarity condition also can be used. So we have a side, side, side. Of course, the notation would be similar here. Use SSS sim for similarity. Again, we're looking at satisfying the proportionality in this case. So we want AB over DE to be equal to BC over EF to be equal to AC over DF. So we are writing this in a very particular way, right? A corresponds to D, B corresponds to E, C corresponds to F. So if we have two triangles that we want to say are similar, we're making sure that these are being, right, these ratios are very particular, not just any two sides. Right? So A, B, C, D, E, F. All right, because we need that specific one-to-one correspondence where the corresponding angles given by the correspondence are congruent. All right. So let's take a look at, let's look at an example in the next video. Probably won't say much about the activity, and then we'll take a look at the Pythagorean theorem as well. So we'll say that's good for now. It's been decently long video already. So thank you for your attention, and I'll see you guys shortly for one more video.